What if we can enhance the power of your processor in lieu of it working at a fraction of its potential like today? This requires better storage memory. This code shows what the 3D XPoint tries to do, which is finding a way to a better storage systems. 3D XPoint is made by a collaboration between Intel and Micron. First, we need to talk about the two types of memory, volatile versus non-volatile. Volatile memory does not save any data after power cutoff but is fast. Example, DRAM and SRAM. Non-volatile memory saves data even after power cutoff but is relatively slow. Example, SSD and hard drive. Here we can see the memory hierarchy, where everything above and including the physical memory is volatile and fast, but everything below it is slower and non-volatile. Here is where this new technology comes in. The crosspoint is fast, inexpensive, and non-volatile, which places right in between physical memory and the solid-state memory.
Now, before we take a look at the 3D crosspoint, we will have to look at a NAND flash cell. As current travels through the control line into the transistor, electrons are pushed through the gap between the control gate and the floating gate. This represents a zero value for one bit to change. Then this value voltage of the opposite polarity is then fed into the control gate, drawing the charge from floating gate and thus changing the bit's value to 1. Now looking at the 3D crosspoint memory cell, we can see that it is made up of four major components: a selector, which is colored in yellow, memory cell, colored in green, a word line which comes into the middle, and a bit line which is above and below the middle line. Then the big idea of the 3D crosspoint is that the current travels through a specific word line and a bit line to read or change the value of the cell where they intersect. This design removes the need for transistors, which makes crosspoint faster, easier to read, write, and also cheaper to produce. The three-dimension aspect is there to improve the storage density by stacking cells on top of each other, making more data storage possible. How does the 3D crosspoint work? Each cell stores a single bit of data, it either represents a 0 or 1, through a bulk property change in the material of the cell, which changes the resistance level of the cell. The cell can now occupy either a high or low resistance state. Applying voltage on the word and bit line, they can be accessed for read and write operations by varying the amount of voltage sent through the selectors. Now going into specific operations, for the write operation a specific voltage is sent through the wires around both the memory cell and selector. This activates the selector and allows the voltage to go through the cell to initiate the bulk property change. On the other hand, for the read operations, a different voltage is sent through to determine whether the cell is in a high or low resistance state. An important point to highlight is the difference in reading methods of the NAND and crosspoint. Because of the design of the NAND flash, single cell values cannot be individually changed. Instead, cells are stored in clustered code blocks that must be completely erased and rewritten in order to change a single bit value. Currently, this is possible to complete in real time thanks to the speed of the NAND. This shows the major advantage that the crosspoint architecture has over the NAND, since it allows for the individual access to each cell and can independently change values without disturbing other data, making the change much faster. How much faster, to be precise? Well, Intel estimates that the crosspoint will operate up to 1000 times faster than the NAND technology we have currently.
This remarkable change is necessary to keep up with the rapid data growth that the world experiences daily. Every day, massive amounts of new data is generated, and by the year 2020, it is estimated that the total amount of data produced worldwide will exceed 40 trillion gigabytes. Found by a study from Digital Universe, which is a free online information service. However, in order for this data to be useful, it must be stored and analyzed efficiently. Experts speculate that all sorts of computer-related fields will be influenced by crosspoint, from video gaming to digital media production to supercomputer genome sequencing to simply having instant access to every program on your laptop. The possibilities of 3D crosspoint are almost limitless, and with it, we may soon reach a future of computing thought to be decades away. Intel expects the 3D XPoint Optane SSD will be used for high-performance storage and caching, as well as to extend and replace memory. According to the company's projections, users will be able to increase server memory by as much as 8 times and displace DRAM by as much as a 10-to-1 ratio for select workloads. Intel has provided three ways to extend memory with 3D XPoint Optane SSDs: via an operating system paging mechanism that moves data out to the PCIe attached SSD when DRAM fills for a workload, via optimized applications, and via Intel's memory drive technology supported on its Xeon processors. In the future, it will be possible to extend memory with the 3D XPoint DIMMs that Intel plans to release. Observers speculate that the 3D XPoint Optane, and particularly Optane NVDIMMs, will be used to expand the apparent size of DRAM, enable bigger, more effective databases, help overcome big data network bottlenecks, facilitate high-performance computing applications, extend memory and boost instance storage performance in the cloud, provide the storage capacity and speed that hybrid clouds need, and possibly serve as a primary memory tiers in hyper-converged systems.
Recently, 3D XPoint Intel Optane SSDs were released into the market. Experiments were performed in Nankai University in China on an Intel Optane SSD in Linux, a non-virtualized physical environment, as known as PE, and in QMU, a virtualized execution environment, as known as VE. For comparison, each experiment was also performed on a NAND flash-based SATA SSD. Computer systems such as storage systems typically use multiple levels of indirections, owing to the high flexibility demanded for system expansion. However, the communication among different layers will inevitably result in extra performance overheads, thus increasing the result latency. The following two diagrams show the latency breakdown when using NAND and Optane in both PEs and VEs. As expected, using Optane decreases the latencies in both environments. The overall latencies will decrease by 67% and 89% in PE and VE respectively. The following diagrams show how Optane behaves regarding the basic metrics of latency, IOPS, and bandwidth by making comparisons with two kinds of devices, NAND and RAM disk, in both the PE and VE. In the PE, as expected, Optane achieves lower latencies than NAND, with a reduction of 67.4% on average for all four request types. RAM disk is the fastest device in all cases, owing to the more rapid memory speed obtained by using DRAM. However, Optane is only 5 times slower than RAM disk on average, while NAND is 10 to 40 times slower than RAM disk. Although RAM disk has the best bandwidth between each of the memory types, the performance boost by using Optane compared with NAND is still meaningful. The higher bandwidth of Optane indicates it can be used as persistent file cache in offline workloads, such as backup systems. Also, higher bandwidth may change optimization policies of some storage services, like transparent data compression, data deduplication, and erasure coding. Now, the following diagrams show how Optane behaves in real-world applications with different configurations. MySQL was selected, a widely used relational database management system, to perform the tests. 20 gigabytes of data were generated, a 32 megabyte file cache was used, and 16 client threads are connected to MySQL. The performance is measured in transactions per second. The higher, the better. Optane still does much better than NAND in all situations, but in the VE, the transactions per second of Optane decrease much more than NAND, which is caused by the large virtualization overheads. The following table lists the best page size for NAND and Optane. For read-only situations, it is 16 kilobytes for Optane and 8 kilobytes for NAND in both environments. and in the VE, the best page for Optane is smaller than that in the PE. So the advantages of using Optane SSDs is that it is much faster than NAND memory. It is inexpensive since it packs lots of the memory element and is denser, which makes it cheap, and it is non-volatile while DRAM is volatile. And its disadvantages are that it is slower than DRAM and it is still expensive relative to NAND. So in conclusion, this technology will not replace any of the DRAM or NAND, but will be working as a midway compromise placed between the two.